we convinced ourselves in the last lecture that we need little more decay in f hat of n in order to address the problem if f is continuous at a point, then whether the Fourier series converges to f at that point or not. So, this suggests us to define for an integer, fixed integer k belongs to z, define delta of k n, this is equal to 1 by n k plus 1 n f k plus 1 n minus k n f of k n minus k n of this. So, now if f is a Riemann integrable function and continuous at x naught, let me then put it as lemma 1, then delta k n convolution of f at x naught, this converges to f of x naught. So, the proof is that delta k n convolution of f at x naught, this is equal to k plus 1 f of k plus 1 n convolution of f at x naught minus k times f of k n convolution of f at x naught. Now, this is a fair kernel. So, this converges to k plus 1 f at x naught minus k f at x naught. So, which is nothing but equal to f of x naught. So, this is true. Now, the same thing what we know that we can add this, suppose if f is continuous everywhere, then what we have proved that the fair convolution with the fair kernel, the Cesaro sum, this converges to f uniformly. So, hence we can write if f is in C minus pi to pi, then delta k n convolution of f converges to f uniformly. Now, the next thing what we would like to see is that the lemma to let f is Riemann integrable function and mod of f hat of n is lesser equal to c times mod of n not equal to 0, or even for that matter for large n, then mod of delta k n convolution of f at x minus s sum m f of x, this is lesser equal to 2c by k, where k n is lesser equal to m is lesser equal to k plus 1 n. So, this as a matter of fact we had observed that in our previous lecture, if I write k n convolution of f of x minus s m of f in terms of the Fourier series, then this is going to be lesser equal to, because this delta kn is flat on this. So, therefore, this is going to get cancelled with the summation over f hat of n. So, what we have got is essentially k n is less than mod n lesser equal to k plus 1 n and mod of f hat of n, because mod of e to the power I n x is 1, and in between minus k n to k n, S and f is going to get cancelled, because this is going to take k delta k n is just hat is just 1. So, therefore, only remaining part is that k n to k plus 1 n, because that is where the delta n is supported, or minus of k plus 1 n to minus of k n. Only this is going to contribute, because in this delta k n is nothing but the constant function 1. So, S m will go away. So, here in this case this will look like, so what I mean to say that delta k n convolution of f at x, this is equal to summation mod n lesser equal to k n f hat of n e to the power I n x plus summation over k n is less than mod n lesser equal to k plus 1 n, then some 2 to the power 1 minus mod j by k n plus 1, this calculation sum f hat of n e to the power I n x. Okay. So, now whatever that quantity is, that one can calculate the delta k n hat very easily. So, here if we calculate, then what we are going to get outside k n, this is not going to contribute. So, this one would be this alpha n, this is equal to 1 minus mod n by k plus 1 of n. This is precisely what your calculation. So, irrespective. So, now what it is given that this is f hat of n is lesser equal to c by mod n, because we are taking out the 0 outside. So, now this would be lesser equal to 2 times c will come out summation over n is equal to k n plus 1 to k plus 1 n 1 by n. So, because that is the mod n. So, now this certainly is lesser equal to 2 c, and there are n number of interval, and n is greater or equal to 1 by n is greater or equal to k n plus 1. So, 1 by n is lesser equal to 1 by k n. So, this is equal to 2 c by k. As we observe that if we are taking our k to be large, then this difference of this delta k n convolved with f minus of s k n of f, this is going to be very small, and that is what probably we wanted. Now, we are kind of state our first result in this direction. So, this is we will call it again the lemma. Let f hat of n is lesser equal to c by mod n for n not equal to 0 or for large n. Then what we can, if f is continuous at x naught, then S n f at x naught converges to f of x naught, and also if f is continuous everywhere if f belongs to C of minus pi to pi, then S and f converges to f uniformly. So, this already we have discussed the proof of this. For the sake of completeness, let us write it down. So, the proof, let epsilon greater than 0. Now, choose k such that k is an integer such that k is greater than 1 plus 4 c by epsilon. Then by lemma 1, we can find n sub naught which is greater or equal to this k such that delta k n convolution of f at x naught minus of f of x naught, this is less than epsilon by 2 for all n greater or equal to n sub naught, because this converges as f is a continuous function at x naught. This is a good kernel, that is what we had seen. Now, suppose your m is greater or equal to k times n sub naught, then k plus 1 n which would be greater than m, which would be greater or equal to k n for some n greater or equal to n naught. Therefore, by lemma 2, we get mod of S m f of x naught minus of f of x naught. This is lesser equal to delta k n convolution of f of x naught minus of S m of f of x naught plus delta k n convolution of f at x naught minus of f of x naught. So, now the second quantity is less than epsilon, and in the first quantity by lemma 2 is going to be lesser equal to some constant 2 c by k. By our choice of k, this is going to be less than epsilon by 2 plus epsilon by 2, which is less than epsilon. This is where the clever choice of k is needed, because in the lemma 2 what we have is that this is 2 c by k. Okay, so, then this is, and for f is a continuous function, then we know that this convergence is uniform, and this is exactly the same proof is going to hold for the second part. So, as a consequence, already we have proved the theorem, but let us write down the theorem. This proof we have seen in a different way. Now, suppose in particular, suppose f is C1 of minus pi to pi, continuous function such that the f is differentiable and f prime is still continuous, then S and f converges to f uniformly. Why? Because we know that if f is in C1, then f hat of n is mod of f hat of n is lesser equal to some constant by mod n. Just taking the derivative, this is what we have seen time and again. So, now this satisfies the condition of the lemma 2, and once it is there, then by the lemma, this lemma, let us call it as lemma 3, then this lemma gives us this theorem in particular. Okay, so this what we have got, that the crux is that we cannot say if f is a continuous function, then the Fourier series converges at that point or not. However, if it is continuous, if it is 0 in an interval, if it is vanishes, we are localizing this, then S and F converges to 0. Now, if we are given with just continuity and if we have a decay condition on f hat, then S and F converges to F at that point. Okay, but unfortunately, although this is a bit satisfactory, but let us we do not get the continuous function all the times. Not all functions occurs in nature, they are continuous. So, we need to deal with discontinuity, because that is the truth of life. So, now how to deal with the discontinuous function, and whether what can we say about the convergence of the Fourier series. One of the toy example what we have seen is the sawtooth function, that is, so recall the sawtooth function f of x, this is equal to x, it is a 2 pi periodic if x is not equal to pi and 0 otherwise. That means, this is what we have seen, minus pi to pi, f of minus pi is equal to f of pi, because it is a 2 pi periodic function. So, in the open interval, this is nothing but the function x, and at the pi it takes the value 0, 0 here. So, that is what is our function, we have seen it and we have computed the Fourier coefficient of this. Then what earlier we have seen that f hat of n is equal to 0 if n is equal to 0, and this is equal to minus 1 to the power n plus 1 by I n if n not equal to 0. This is what we have computed earlier. So, therefore, as you can see that here f hat of n, this is less or equal to 1 over mod n if mod n is not equal to 0. We have the decay condition what we are imposing with the continuity, because continuity plus decay gives the convergence. Now, here we have a decay condition, but it is not continuous at pi or minus pi. Then what can we say about the convergence? Now, for example, then S and F of x, this converges to f of x for all x belongs to minus pi to pi, because in this open interval this f is a continuous function and it has a decay. Therefore, by the previous result what we know that this Fourier series converges. Now, what about what happens at x is equal to pi? So, let us write down the partial sum S and f at x, this is equal to, so summation over n minus n to n, n not equal to 0, minus 1 to the power n plus 1 by I n and e to the power I n x. Now, break the sum into the positive integer and the negative, this means break it into minus n to minus 1 plus 1 to n. And now, if you look at this, then this is going to be what we are going to get, that this is summation n equal to 1 to n minus 1 to the power n plus 1 divided by I n e to the power I n x minus of e to the power minus of I n x. Okay. So, now this is equal to 2 I sin x. So, this becomes 2 to the power 2 into n equal to 1 to n minus 1 to the power n plus 1 by n sin n x. So, therefore, S n of f at pi, this is equal to 0. This is true for all n, right. So, therefore, this is going to converge to 0 as n goes to infinity, right. However, so now this is, and this is what the value, what is happening is the, because we are giving the value at 0, therefore, this is converges to 0. Now, what happened if we are giving some other value, and this actually is a kind of the typical of quite a large class of function. This is what we can see. Okay. So, now we are ready for the lemma for the large class of function. Let f be a Riemann integrable function with mod of f hat of n is less or equal to some c times the decay is there as for large n. And now, suppose f of pi plus, which I am defining that limit x going to pi plus f of x and f of pi minus, which is equal to limit x going to pi minus of f of x exists. So, then S n f of pi, this converges to f of pi plus f of pi minus divided by 2. It goes to the average. If it is taking the different value, then it is going to. So, now let us get into the proof. So, now what we are empowered with the convergence of the Fourier series with, for continuous function having a decay in the Fourier coefficient. Now, what we are going to use is that we will convert this f into some continuous function plus something, and then we will do our analysis on this continuous function, and hence we are going to conclude the result for us. This is a powerful tool which is quite often used in analysis. Now, what I will do is that let, or rather define g from minus pi to pi to complex number by g of x, this is equal to f of x plus 1 by 2 pi f of pi plus minus f of pi minus. Remember that these two quantity exist, and then I hit that with the sawtooth function when x is not equal to minus pi to pi, and which is equal to the average of so, what is h of x? H of x is equal to x if x belongs to minus pi to pi and 0. That is the sawtooth function 2 pi periodic. So, now as you can see that limit x going to pi minus or pi plus for that matter. So, of g of x, this is equal to, this is f of pi minus, this limit is going to be there, plus 1 by 2 pi f of x pi minus. Now, h of x is x on minus pi to pi open interval. So, if I am taking the limit of this h of x, then this is going to be pi, right. So, this is pi. Therefore, this is equal to 1 half of f of pi plus f of pi minus. This is exactly nothing but the g of pi. Again, similarly, we can show that x goes to pi plus g of x. This is again g of pi. So, g is a continuous function. Therefore, so g is continuous function, g continuous, and if you look at g hat of n, which is nothing but this is f hat of n plus h hat of n has a decay of some constant by n. So, therefore, easily this is lesser equal to some constant by mod n, because f hat of n is given with that decay, and therefore, S n g of pi, this goes to g of pi. Now, S n g of pi, which is equal to, so now we know that S n of h pi, this goes to 0, that is what we have seen. Hence, this is S n of g pi converges to g pi, S n of g pi is S n of f pi plus half times this. So, therefore, this is going to be S n of f of pi. If we are writing, then this converges to g pi, which is equal to 1 half of f of pi plus f of pi minus. As you can see that S n what S n of g is equal to S n of f plus 1 by 2 f of pi plus minus f of pi minus and S n of h. Now, this converges to 0, therefore, S n of f converges to S, which is equal to S n of g, and which converges to g of pi, which is nothing but the average. So, one can see that there is nothing very there is nothing wholly about the x equal to pi. This we can do it for any arbitrary point irrespective of f. What essentially the idea is that you just translate the function. Now, when you are translating the function, you can convert the x into pi, move that further, and then what you are going, if you are translating and taking the Fourier transform, then the Fourier transform is going to be heated only with e to the power I n x, and that is 1 and f hat of n. So, the decay is not going to be hampered if we do the translation. So, with the translation trick, one can actually replace this pi by some other method. Thank you.